Okay, I'm going to try and do a cleaner job of presenting density-dependent growth than I did in class yesterday. I think I confused a lot of you because I messed up one of the steps in the math, then I had to backtrack, and that seemed to throw most of the class. So I'm going to do this again in the relaxation of my office so that I can do it hopefully in a more understandable way. So when we think about population growth, we can think about population growth as being of a density independent variety where the change in population given some change in time is just actually due to the per capita growth rate multiplied times the number of individuals that are in the population. And we can add density dependence to this by introducing this idea of carrying capacity such that this part of the density dependent equation represents the fraction of carrying capacity that remains after a certain number of individuals have used some of that carrying capacity up. And so R is a constant. Generally, when we're doing the model, we consider K to be a constant, but K can fluctuate as environmental conditions change. But K is basically carrying capacity. And so introducing this idea of carrying capacity into the equation allows us to account for the fact that populations can't grow in an unrestricted way, which is what happens in density independent growth. And so carrying capacity is expressed in the number of individuals. So that's the units that it is. It's the number of individuals that a given environment can support for an indefinite period of time. And so the question that we have is where does this come from? Where does K come from? And I'm not going to ask you to do this derivation on an exam or even reproduce it yourself, but I want you to see where it comes from so that you have some understanding of why this is the case. So let's go back and reduce this equation back to the density independent version. And remember that we can rewrite this as the per capita birth rate minus the per capita death rate times N. That is what R is. B minus D is equal to R. And once again, these birth rates are presumably constants. But as constants, they don't get affected by population size. Population size just gets multiplied to them, and the population grows exponentially. Well, we can make these birth and death rates subject to the limits of population by basically saying, well, what was the birth rate under density independent conditions, and then subtract from that birth rate some figure that reduces the birth rate as it is affected by density. And so here we have a constant A multiplied times N that is subtracted from the birth rate that you would assume would be happening if the population were growing in a density independent way. We can do the same thing with the death rate, where we replace the death rate with the death rate assumed under density independence, plus some constant related to the density of the population. So this constant gets added to the death rate because as population size increases, then the death rate increases. This unit here gets subtracted from the birth rate because as population size increases, the birth rate goes down. So now what we can do is we can just take these two expressions and we can put it in place of B up here, and we can put this one in place of D up here. And so the change in population size given some change in time is equal to B under density independent conditions minus AN minus D under density independent situations plus Cn, and that whole thing is B minus D now, which is multiplied times N. And I'm going to drop these little di's simply because they're just cumbersome to write, but just remember that they're the density independent birth rates and death rates. So what we can do with this now is we can start doing some math. One of the things that we can do is we can assume that we want to know what N would be. What is the population size when the change in population size given some change in time ends up equaling 0. This is a mathematical trick that allows us to set this side of the equation to 0. Now we can get rid of population size on this side by multiplying times 1 over n, multiply times 1 over n. This is still 0, but the effect of that is it gets rid of population size. So now we just have these two expressions on the right-hand side. Now you'll notice that these are rates, whereas these are things that get multiplied times population size. And so one of the things that we can do is we can just gather terms. And so this would be B minus D minus A times N plus C times N. So we've gotten these terms together. Once we've gotten those terms together, we can actually factor out N over here. This is all still equal to 0. Once we've done that, we can add this to both sides, because what we're trying to do is we're trying to isolate population size by itself, and then we can divide by A plus C and divide by A plus C. And this gives us N equals B minus D over A plus C. And that is the population size where the population growth rate goes to 0. And so it's just simple symbolic math working through the situation. What this basically says is, as population gets bigger, birth rate is decreased by some amount. As population rate increases, death rate increases by some amount, and those amounts are determined by A and C. So what I want to do is draw a little graph for you that illustrates kind of why this is working this way. We can draw a graph where on the y-axis are the rates, and on the y-axis is population size. And we can use the red marker for death rate, and in the tortoise example, we had a per capita death rate of 5. And we had a per capita growth rate of 6. Okay? And so we can write an equation that relates the birth rate that you started with to population size from essentially 0 individuals to a lot of individuals, whatever a lot means. And in this case, the equation that does that is the equation that is a line, and that equation is B minus AN. And we can actually put numbers on that. The birth rate in this case started out at 6. We can say, well, it's reduced a little bit by population size, but not by a ton. We can do the same thing with death rate. And death rate started out at 5, and it gets increases, let's say, by 0.001 times n. That's once again just giving you the death rate plus C times n. So these are the lines. Those things that we derived earlier were actually the lines that describe this. And where these lines cross, this is where carrying capacity is. And that is what this expression is carrying capacity. Now, one of the ways to think about these numbers A and C is to think about them as measures of the strength of intraspecific competition, the strength of individuals of the same species competing for resources. And so if A is small, then intra-specific competition is weak. What that means is that individuals aren't really competing that strongly for resources, and so you can pack a bunch more individuals on the landscape than you could if A is large, in which case interspecific competition is strong, resources are more limited, and as a result, you can have fewer individuals. So as A gets big, K gets smaller. Same thing with C. If C is small, the death rate isn't influenced by population size very much. And so as a result, competition is weak and carrying capacity is bigger because you can have more individuals on the landscape. But as C gets larger, the denominator here gets larger and carrying capacity goes down. Okay, so we can actually show this by altering this equation. Let's say that instead of having A and C having them equal 0.001, we can actually have them equal 0.01 instead. What that does is it makes the rate at which death increases with increasing population size much steeper, and it makes the rate at which births decrease with population much steeper. And what that does is it brings this intersection line in so that K is now much smaller because the strength of intraspecific competition is now stronger. And so this is where K comes from. It's due to these coefficients that basically relate the size of the population back to how birth rate and death rate is being manifest in this population. So that's where it comes from. So let's just leave that over here on the side for a few minutes and go back to our original equation. Once again, we had dn over dt equals r times n. We realize that this is birth rate minus death rate times n. And we realize that this can be expanded to include population limitation by basically doing this as b minus an minus d plus cn, and that is all multiplied times n. Now we're not going to set it equal to 0. We're actually just going to do some manipulations on this to see if we can come up with a simpler equation for this. And so the first thing that we can do here is inside the brackets, we can gather terms like we did before. And this is where I messed up in class yesterday. Not only that, once we've gathered terms, we can actually factor out this in like we have before. So this is kind of a repeat of what we've already done. But then what we did, once again, I think this threw you off a little bit, is we can say that 1 can be multiplied times both sides and not change the equation at all, but we could express 1 in any of the terms that are in this equation. And so let's just express 1 in terms of b minus d. And so it would be b minus d over b minus d. And so here at the beginning, we can multiply both sides by b minus d over b minus d. That's 1 multiplied times this thing that is in brackets, and it'll be just multiplied all the way through there. So We can think of this as multiplying this all the way through, but the other thing that we can think about this is we can think about this as b minus d multiplied times 1 over b minus d multiplied times b minus d plus n times a plus c times n. And what we get when we do that is this cancels out, leaving you with a 1 here, and this gets multiplied into here, which is b minus d. And so you're left at the end of this with b minus d times 1 minus a plus c over b minus d times n, all of that multiplied times n. And this equals the change in population size given some change in time. We can simplify this a little bit because what is b minus d? B minus d is r. R times n is kind of what we started with at the beginning. So r times n is the density independent portion of this, and this represents the density dependent portion. So let's go up here and rewrite this. So all I did was I took this, rearranged it a little bit, and rewrote it up there. So now I'm going to get rid of this so that we are not confused and distracted by it. And then if you look at this expression right here, you see that this expression is the reciprocal of this expression. B minus d is in the denominator, a plus c is in the numerator. Here, b minus d is in the numerator, a plus c is in the denominator. So this expression here is just basically, if this is k, this is 1 over k. And so we can rewrite this equation such that change in population size given some changes time is equal to the per capita growth rate multiplied times population size times 1 minus n over k. And I prefer to write this as r times n times k over k, which is just 1 expressed in units of k, minus n over k, so that we can rewrite this as r times n times k minus n over k, because this particular expression is the expression that is of interest to us, because that's the expression that reduces the growth rate that you would experience under density independence when you have density dependence. And k minus n over k is a fraction, but it's a very specific fraction. It's the fraction of k that remains after a certain number of individuals, n, have used some of it up. So if carrying capacity is 100, and we have one individual on the landscape, then that basically means that 99% or 0.99 of carrying capacity is left over. So you're actually going to have a population growing at pretty close to the population growth rate that you would experience under density independent population growth. But if you have 10 individuals, the population will only be growing at 90% of what it would be growing if it was under density independence. If you have 50 individuals, it will be growing at 50% of the rate. If you have 99 individuals, it will be growing at 1% of the rate that you would expect under density independent conditions. And so this is what enables us to incorporate density dependence into this population growth curve, the growth equation. And when you do that, it leads to a different dynamic of population growth. Before, we had populations time is going from the past to the future, and population size is going from 0 to a lot. And under density independent growth, we actually have population just growing exponentially. It's presumably forever. But under density dependent growth, it grows slower from the very beginning, and then it comes and it levels out, and it's going to level out at whatever carrying capacity is. And when you're halfway to carrying capacity, that's where population growth rate is actually the highest. It's lower than that before you get to halfway to K because population size is not very big, and it slows down after you get past that halfway point because now density dependent factors are actually kicking in and limiting growth. So hopefully this was a clearer presentation than what I went through in class yesterday, and hopefully this will help you out some. I'm not going to ask you to do any of those calculations, but I do want you to know this equation. And now I've cluttered it up quite a lot. I want you to know this equation, dn over dt equals r times n times k minus n over k. And I want you to know what that means in terms of population growth. And I think that one of the ways in which to get you to know what that means is to actually show you where that equation came from. So hopefully you found this useful. And if you didn't, then by all means come by and see me in my office.